In our study, we were interested in how system performance is affected by calibration method, sample size, and sampling variability in likelihood ratio-based forensic voice comparison. Now, in forensic voice comparison, experts often need to compare the speech samples from the unknown offender and the known suspect to see to what extent these two samples come from the same person or different people. Now, in recent years, the likelihood ratio framework has gained increasing acceptance as the appropriate approach for forensic evidence evaluation and expressing expert conclusions. Meanwhile, there's growing pressure on experts to empirically validate their methods and system performance. In doing so, there are established procedures which normally involve 3 sets of data, that is training, test, and reference, and 2 stages. So in stage 1, the acoustic features got extracted and modeled into same and different speaker models to generate scores. Now in stage 2, the scores are being calibrated into interpretable likelihood ratios. Now it seems that the data-driven approach is objective. However, there's some subjectivity going on here. For example, the researcher has the degree of freedom to choose which acoustic features to be extracted and which statistical models to be used. In our study, we were interested in how different choice of calibration methods would affect the system performance. Now, previous studies have shown that the system performance can be affected by the size of sample we used, that is how many speakers we use for each of the training, test, and reference data, as well as the configurations of the training, test, and reference data. Now, the configurations here can be systematic. For example, we can use speakers with same or different accents for each of the data sets, or the configurations here can be just random. For example, we randomly sample speakers from a given population and test the system performance. It seems that the sampling variability is inevitable regardless of the sample, regardless of the size and the configurations of the training and test and reference data. Now the question is, how is system performance affected by sampling variability? And can calibration method reduce the level of uncertainty? Previous studies have also tested the effectiveness of different calibration methods. However, they either used the limited sets of data or they assumed that the score would follow Gaussian distributions. Now, given the limits of the sample size in the real world, how does the system perform when the scores are skewed and sample size is limited? Now, can we incorporate the uncertainty into ELUB computation itself? Can certain calibration method reduce the level of uncertainty when the sample size is small? Now, we simulated scores from skewed distribution to test the 4 calibration methods, that is logistic regression, empirical lower and upper bounds, regularized logistic regression, and the Bayesian model. Aiming to investigate the overall system validity and the reliability of the system validity. Apart from the logistic regression, all the other 3 methods claimed to incorporate the uncertainty into ELUB itself, such that the ELUBs will be closer to 1 when uncertainty is high. So in our context, when the sample size is small. The skewed scores were simulated from the acoustics of field of pulse, where we used the 90s standard Southern British speakers from the diverse corpus. The quadratic curves were fitted to F1, 2, 3, and F0. The coefficients of the quadratic curves were used as the input for MVKD to generate speaker models. Now here shows an example of the quadratic curves fitted to 5 tokens of F0, 1, 2, and 3 from the speaker 114 from the diverse corpus. Now the scores were simulated based on the distribution parameters shown in the table here, and the skew normal distribution function in R was used. Here, the plot shows an example of simulated the same different speaker log scores using the parameters in the table here. Now, the training and the test scores were sampled 100 times using different sample sizes from 20 to 100 speakers with a 10 speaker increasement. This result in 20 to 100 same speaker scores and 380 to 9900 different speaker scores. The calibration was replicated 100 times using each of the 4 calibration methods for each sample size. Now here shows schematic process for score simulation and ELUB computation. So the training and test scores got simulated based on the parameters and then calibrated into likelihood ratios, then to generate the Cllr for system evaluation. Now the system validity was evaluated using the mean Cllr out of 100 replications, and the system reliability was evaluated using the Cllr range, that is the maximum Cllr minus the minimum Cllr in 100 replications. So a Cllr of less than 1 indicates that the system is capturing some useful information, and systems with better performance would yield both lower Cllr mean and range. Here shows the result. The x-axis is giving the different number of speakers we used, and the y-axis gives the Cllr values. So the black dots and the dashed lines are the mean Cllr and the Cllr range across different sample sizes. In terms of system validity, it seems that the logistic regression consistently gave the best, the lowest mean Cllr across the different sample sizes compared to the other 3 calibration methods. In terms of reliability, so the regularized logistic regression and the Bayesian model seems to outperform the other 2 calibration methods, as indicated by the dashed line here. The Cllr range is quite low, about 0.1 or even lower across different sample sizes. However, for logistic regression, the system seems to be less stable when the sample size is small, and more stable when the sample size is large. For ELUB, it seems to give the worst performance in terms of both validity and reliability, and the Cllr range is kind of fluctuating across different sample sizes. So based on our results, different calibration methods need to be considered when the scores are skewed, especially when the sample size is small, and both system validity and the reliability need to be reported. For example, the logistic regression consistently gave the lowest mean Cllr. However, it has a more fluctuating Cllr range compared with regularized regression and the Bayesian model. Now, it is our opinion that the expert decision should be driven by lowering the uncertainty, rather than the higher validity, that is the potential of producing a very low Cllr. Now, thank you very much. If you got any questions, feel free to drop me an email. Bye.